Okay, AP kids, hopefully this audio is a little bit better than the last time. Because we're doing so much lab this week, I thought that it might be more efficient for us to go through some of these reactions that are review from regular chem. So hopefully it should look very familiar. Most you've actually probably had to kind of review to be able to do the worksheet number 1 and worksheet number 2. So if you want, feel free to kind of skip ahead through the video and get the notes down. If it all makes sense to you, go as fast as you feel like you're able. But I'm going to kind of walk through and highlight some of the important things as we're going through. So anyways, we're talking about classifying chemical reactions. We already talked about redox, which is just a phenomena that happens when there's a specific reaction where electrons are gained or lost. Our first main type of reaction is a combination or a synthesis reaction. You probably hear mostly me say synthesis, but either work. With a synthesis reaction, we've got several different types. The simplest is element and element makes a compound. These are always redox reactions. If you look at the binary ionic compound here, binary meaning just 2 ions, sodium has an oxidation number of 0, chlorine has an oxidation of 0, and here in this compound this is +1, -1. So you can see that the sodium itself is being reduced and the chlorine itself is being the sodium is being oxidized because it is going from a 0 to a +1. It's losing that electron, and the chlorine is gaining an electron and being reduced. The example below is for covalent or molecular. You can see that the nitrogen and the hydrogen make ammonia. In both cases, element plus element makes compound. Here again, we'd have 0 and 0, and they would be non-zero on the right side. So we would in fact have a redox reaction. Second type, element and a compound turns into a more complex compound, or a bigger compound, you can say. So this compound here will always be more massive because it's being added to by whatever the element or elements that are being added in. So here we got PCl3 and Cl2 makes PCl5. Now I wouldn't expect you to be able to predict these products on the right. I wouldn't expect you, without those products given, to be able to figure out them from the stuff on the left, unless I kind of gave you a basic structure of what's happening here. You can see the one on the bottom is not currently balanced, so we have to do some balancing there. So we'd go, let's see, a 2 here to make 6, and a 4 there to complete the 6 oxygens on the left. Okay, still a redox reaction. In this case, though, this would be 0, -2. So the oxygens here are not being oxidized, but the oxygen from the 4O2 is being reduced, and then so I would assume that the sulfur is being oxidized if you wrote in those oxidation numbers. Scrolling down, third type of synthesis reaction, compound plus compound makes another compound. You know, these are never going to be redox reactions. We look here, calcium oxide, we got +2, -2. Carbon dioxide, oxygen's a -2, leaving carbon with a +4, makes calcium carbonate. Now if oxygen's a -2, that's a total of -6. Calcium's a +2, that still leaves carbon as a +4. So even though the reaction happened, even though we broke the bonds in the compounds on the left and reformed in a new compound on the right, electrons were not actually gained or lost by any given element. So that's our first one. So first we've got combination reactions. Second, we've got decomposition reactions, which again I think we briefly touched on in class. These reactions are always endothermic, meaning that they absorb energy. When we talk about changes in enthalpy and whatnot, we'll see some reasons for that. They are always redox, basically for the reason that they are the reverse of synthesis. So this example here, you've got compound making elements. Those elements will have redox numbers of, or oxidation numbers of 0. They are non-zero on the left in that compound. Could be a compound, makes a compound and an element, so it doesn't quite break apart into its elemental components. There's still a compound here left, you can see in the KCl. They are still redox though. If you're going to look at this, you can see that the potassium's +1. Here this oxygen is 0 and -2. This is -1, and the chlorine on the left is left to be +5. So we have the chlorine is actually being reduced while the oxygen is being oxidized and increasing its oxidation number from -2 to 0 by losing 2 of its electrons. Third example, again, basically just the opposite still. Compound makes compound and compound. These ones may or may not be oxidation reactions. Just as a quick check here, this is basically the same one as we had previously, so we know that that's not a redox reaction because all those oxidation numbers stay the same. The one above it though, got -2, +1, -2, That means the chromium here is +3, nitrogen is 0. That's kind of the giveaway there, that there's an element that's 0 on the one side that is not elemental on the other. You can see that the nitrogen here is definitely not in a compound, so it's not, or excuse me, definitely in a compound, so it's not going to have an oxidation number of 0. We know that the hydrogen's +1. Now, the way that I would do this, because technically nitrogen and chromium are unknowns here, but we know that this nitrogen comes in an NH4+. That's an ammonia. So if we know this is +1, we can actually figure out this nitrogen has to be a -3 there on the left. You know that chromate's a -2, so we can figure out that's got to be a +6. So you can see that in this top example, chromate is being reduced, or chromium, excuse me, and then the nitrogen is being oxidized. Oh, drawing a straight line there instead. Well, oxygen and hydrogen are neither being oxidized or reduced. Third type is a displacement reaction. So there's two types, single and double. Okay, I will probably use the word replacement in class, single and double replacement, more than displacement. They are always redox reactions, always, 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 every time. In single replacement, you always got an element going into a compound and vice versa. And a double replacement, same is true. I guess actually we're not talking about double replacement yet. We'll get there. These are always redox reactions. More active free element replaces a less active element. So it'll be a more active element plus a compound, and then the more active element will switch into the compound and kick one of those elements out. If the more active element makes a cation, it'll kick out the cation in the compound. If it's an anion, it'll kick out the anion in the compound. The activity series, just for reference, is on page 146. So this is how you know what elements are more or less active. A whole bunch of examples there. Those are all in the notes. But let's take a look at some of the ones that we've got written here. So if you look here, we see zinc, and we've got HCl. Now zinc makes a positive ion, so I'm just going to make notes up top. Zinc makes a positive ion, so we have to compare it to hydrogen, which is also the positive ion here. If you look on the activity series table, turns out zinc is more active, so the zinc replaces the hydrogen. So we get zinc chloride. You'll note that there is 2 chlorides because zinc is a +2 ion, and then that hydrogen is left over, oxidation number of 0, which again is why we end up with a redox reaction, because zinc is 0 here, +2 here, so it lost 2 electrons. Hydrogen is +1 here, and 0 on the product side, meaning it gained 1 electron. And see the net ionic, we split up the HCl and the ZCl3, or excuse me, the Zn and the Cl, and then we canceled out the chlorines to get the net ionic down there on the bottom. Another example here, I'll just leave it for a second. You guys are always welcome to pause the video, but you can see that the sodium was in fact more active than the hydrogen. In this example, it doesn't actually make sodium oxide in hydrogen gas, it makes sodium hydroxide. This is actually, if you've ever seen a video of sodium being thrown into a bucket of water and there being a pretty violent explosion, it's because there's all this hydrogen produced, and this is actually an exothermic reaction. There's a lot of, if I can squeeze it in there, there's a lot of energy produced in this reaction. So hopefully that's a good set of examples. You can see that there's more. Example exercise 91 on page 172. This one is to practice the activity table. I obviously can't put it on the document camera while I'm doing something like this, so if you want, remind me in class and we'll go over some of those. So here's the double replacement reactions. I kind of was lumping them in. I thought they were in one category under the notes. So we've got the displacement, that's single replacement, and then now double replacement. These are neutralization reactions or others. So one example here is an acid plus a base makes salt, and meaning any ionic compound, not necessarily NaCl, unless the base has sodium and the acid has Cl, like sodium hydroxide and hydrochloric acid, and always water. These are not redox reactions, so I think I might have said that earlier when I was lumping it in with single replacement. So these are not redox reactions for the reason that nothing is actually gaining or losing electrons. No reaction is not an option here with single replacement. If the free element is not more active, there will be no reaction. These will always happen, but there's a pretty wide variety of categories here and what could be produced. Taking a look at this first one, we got HCl and barium hydroxide, makes barium chloride and H2O. You can see that the hydrogen replaced the barium, but rather than being alone, the barium also came around and replaced the hydrogen. Ionic equation is split things up. If we were going to do the net ionic, we would cancel out those Cl's and cancel out the Ba's, and we get H plus, and OH makes H2O. Looking down a little bit further, here's an acid base. You can see that this is sulfuric acid and strontium hydroxide. Makes strontium sulfate and water. So there's our acid-base neutralization. Broken up down here. Strontium sulfate, you check the solubility. If it's solid, you leave it as a solid, and then the H2O is there as well. And I think that is all I wanted to go over with you. Oh no, precipitations reactions. So we're not going to continue on to gas formation. That's something that I want to talk about in class about. You're welcome to write it down so you have it. You've obviously seen it now. You can pause it. But precipitation reactions are a category of double replacement reactions when you make an insoluble, meaning doesn't dissociate, doesn't dissolve, solid in a reaction where there was no solid before. Two aqueous compounds make a precipitate, and usually the other is an aqueous, meaning soluble ionic compound. Solubility rules, this is one of the big reasons that we've memorized them. So when you look at those two products in a double replacement reaction, you can identify which one is the precipitate. So we might do some more examples like this in class, but I figured that with the worksheets for homework, it'll be more guided by which ones we have questions on. So hopefully that was helpful. Hopefully this will give us a little bit more time in class to go over those homework questions. I forgot to number the rest of them. There were 4 total. We didn't end up talking about combustion right here, but it is in this, there's 4 in this section. Anyways, I'm rambling. Don't want to take up any more of your time. Hope you guys have a good rest of your evening. See you guys tomorrow.